Hey, Carrington.
Hi.
One second. Problem session something. Well, I think some people might come. Sometimes people come a little later. But we can get started. So questions?
The only real question I had is for 7.4. Are you just wanting like a written description of
Let
like
me
what the points are?
let me share screen real quick with this thing. And then that way I can look at the problem you're asking about. Okay, so problem number 7, you said 7.4?
Right.
1 second, okay. 7.4, is this one?
Yeah.
Okay. Each of the figures in exercise 6.3, find the points that have non-trivial stabilizers and identify the stabilizers. Okay, so let's look at 6.3. Okay, great. Okay, so hold on a second. Let me hi Kale. Oops. Maybe okay. All right. So find the points. Yeah, this is it's a pretty ambiguous question. I'll give you that. That there's, because it's I mean, there are points that are not exactly on the figures that might have non-trivial stabilizers, you know. So like, you know, you could have a point like this that well, I guess this point is, yeah, this has a non-trivial stabilizer given by just, you know, these points from like rotation by, you know, 180 degrees or reflection. Looks like there's some axes of reflection here. So there's some points that are not exactly on the figures. I mean, I think it's a great exercise, but yeah, as far as how to write it down and how to answer it, I'm a little concerned that I don't want you guys to have to redraw these figures or anything and mark it. Maybe if you can like choose one of them, let me ask you guys, I'll give you full credit if you choose one of these, and then just try to, like, I imagine maybe one of these two, so that you can just kind of like sketch it, you know, or at least, you know, sketch like a little region of it, and then identify the points with non-trivial stabilizers. You know, that is something like that might be, I think might be enough. So, I mean, we can look at one of them. If we look at, let's say we just look at the first one, for example. Then you guys, you know, you guys tell me what points do you think might have non-trivial stabilizers of the isometry group that preserves this, the crystallographic group that preserves it.
Would the center of the squares have it?
Right, I think the center of the squares is 1 point, so we could kind of, because, and so what would be the, so okay, let's choose this as one of the points. Um, not sure if it's the only or not. Anyway, let's look at this one for the moment. So for this point, what is this? Let's, if I call this, well, I'll just say stabilizer G sub S for this, for the red point. What do you want to say this is? What do you think?
Are you asking me? I didn't hear the question.
Oh, sorry. I was asking either of you what you think the stabilizer is for this particular red point. What do you think that we have here? The silence was just a precursor to the later silence.
Apparently.
So what can you, I mean, when you ask for the stabilizer, you're saying you're looking at all the symmetries of whatever it is you're looking at that keep that red point where it is. So it's true, this tessellation, I mean, I could take this and I could take this square and I could translate it to this square and that would be a symmetry. I could carry the entire thing and it would give me a translational symmetry. But that's not going to be an element of the stabilizer of this red point because the red point will go here. Right, so we want to ask for all the symmetries that keep that red point exactly where it is. So what do you think?
Well, if like the red point was like the origin, we would like reflect over the X or Y axis.
Okay, so let's ask that question. So if I draw the X and let's say the Y axis.
Or is it not symmetric?
Huh?
I don't think it is symmetric. Never mind.
No, it's all right. But it's good to like kind of ask these questions. That's exactly right. I mean, when I was looking at it, I was thinking, well, what about this axis? But even that axis, even though it just doesn't have that symmetry, because this line would go to that line. And so actually, I don't think there are any reflections here about any axis that goes through the red line that will preserve this thing. Is there anything else? Kale, you said that this would have a non-trivial stabilizer, so there's got to be some symmetry that you see.
It was just a guess, if I'm going to be 100% honest.
Fair enough. So if they're not, if
like a rotation, maybe.
Yeah, right. If we have only, if we learn that if we're fixing a point in the plane and we have an isometry, that it has to be either a reflection or a rotation, one of the two. And so in this case, it has to be this rotation. And well, if there is a stabilizer. And it does look like if I rotate by pi over 2, that everything looks kind of the same. Right? I mean, this will go to this, and so on. And so I think that actually, yes, there's a symmetry here of rotation by any multiple of pi over 2. And so this should be something like C4. Cyclic group of order 4. Maybe, with the standard kind of whatever coordinate system you need to put in there. Okay, are there any others? I've got more colors.
Like unlike the lines with the horizontal rectangles, you could flip it. No, never mind. Never mind.
What about this guy?
Then it would have the same rotation.
It also has a rotation. So of course, you know, I could say, yeah, of course, at every square, there is this stabilizer, and that's true. Because there's a, you know, so I'm not gonna, we can classify them as sort of types here. So let's not worry about every single square, but let's look at this different, this is sort of a different kind of point. Although you're right, the only stabilizer here, I think, is rotation again. I don't think we have any other stabilizers. So I think here we have that this one is also isomorphic to C4. Now, on the other hand, you can see there's some different ones here. I think that might be it. Okay, I don't know. Let's see. I didn't really. Although maybe not. No, I see actually one more.
If you did like the middle of one of the vertical rectangles,
Yeah, middle
would
of
it
vertical.
be 2?
I think that's the what exactly the vertical. Vertical and horizontal. I think both of them will do this. I was looking at the horizontal. You're looking at the other one.
I
But
think
yeah.
it applies, yeah.
Yeah. So I agree. I think these two are also included here. But now, what did you say? You said, what is the symmetry group?
Because it would just be like a 180-degree rotation.
Yeah, exactly. I think you have a C2 here. And similarly with the purple. Good, very good. I'm pretty exhausted, but I think we've exhausted them all. So I don't know, but maybe not. I don't know. You guys. So I mean, of course, again, there's all of the kind of translates of these guys that we have all over the place. But I don't think the other vertices have symmetries. Yeah. No, and there's no I don't think there are any reflections, so I think we're okay with that. Yeah, looks good. Looks good. All right, so yeah, that would be, I would accept just an answer at this level, I think. If you wanted to do a different one, that's fine, but I think doing each and every one is maybe a little too much, especially since you guys have this midterm. Maybe just do one of them. Okay, other questions?
I was having trouble with 8-2.
A2. Okay, let's take a look. 8-2. What? Okay, let's see. Okay. Oh. What is the stabilizer of the coset AH for the operation G on GH? This is a good question. And it's kind of funny, actually. Well, it's interesting because it shows you that in some sense, this isomorphism that we talked about today for G sets with transitive action, it sort of does depend on the choice of point that you take. It's not just like a single isomorphism. So you get different isomorphisms of cosets. In other words, what I'm trying to say is that they're the G set, which is a quotient with left cosets, is not unique. You can have a different subgroup with an isomorphic G set. Anyway, we'll see that with this answer. So that's the stabilizer. So we're looking, what are we looking for? We want the following set. It's the set of elements, G and G. So that G times, he writes it AH, is equal to AH. Now this is just his notation. He puts these kind of brackets around it to think of an element. is a single element inside of this set of cosets, G over H. But this is equal to, by definition, this is just GAH. Right, so we're looking for GAH equaling AH. So this is what we want. What do you think? So if I have two left, so this, let me ask this question. If I have, when is this true? We have had a criterion for this. This is true if and only if what? Two cosets are equal if and only if what? Can you guys hear me?
Is
Yeah.
it just x equals y?
Huh?
Is it just x equals y? Or are you
Well,
looking-
no, that's two. Okay, so let's take a look at an example. So let's say we had like 3z. This is a subgroup of like the additive group here. Okay. So this is an additive group, so the cosets will be like sums. So I want to say, 2 plus 3z is also equal to, I don't know, like 5 plus 3z. Right. So these are two left cosets. They're the same because they both are just the set of integers with remainder 2 when divided by 3. So it doesn't really, I mean, I can choose, I could have put, 8 in there. All right. So all kinds of things. So the key here is, this is a criterion we had a while ago, or I mean, some theorem or something, is this is true if and only if y inverse times x is an element of H. That's true. That's the statement. So look back in the book or in the notes, and you'll find this when we first start talking about left cosets, that this is the way, this is the criterion. So right now you can use that. So if we're searching for something like this, well, this is true if and only if A inverse G A is an element of H. Or this is equal to some H in H. Or, but now if I have this equality here, this is true if and only if G is equal to A G A inverse. Oh, H, sorry, AH A inverse for some A H and H. Or G is in the conjugate of H. This is a group, a subgroup. It's a different subgroup, just the conjugate of H. So this and this, what were we after in the beginning? We're after all such G that satisfied this condition. Well, all such G that satisfy condition are precisely this conjugate of H itself. So that's what the stabilizer is. So stabilizer. This is of AH. So this is what I was trying to say before, is that this is different in general than H itself. If H is not, I mean, if H is normal, then this is just H. That's the definition of normal subgroup. If H is not normal, then this is, generally speaking, not equal to H. So you get different subgroups, but then the set of left cosets are still isomorphic. Does it make sense? Carrington, you?
Maybe, but I don't know.
You're skeptical.
Yes, but it's okay.
That's all right. Okay, yeah, well, I mean, think about it and do look back in the notes for this statement. So, yeah, I mean, non-abelian groups are a little tricky, and so some of the lack of normality is kind of interesting. So, I mean, another way of thinking about it maybe is just to say, you know, I mean, what happens if what happens if we do have something like this? I mean, then G times AH is A inverse AH. G equals AHH, right? Because you get that cancellation, but H times H is still H, right? So this is AH. Right. So this if this is true, then you clearly can see that it is in the stabilizer. But sort of the converse is also, like, it has to be. If it stabilizes the coset, then it has to be a conjugate of some element of H by A. Is that it? You guys good?
Yeah, I think that's all I had for now. I haven't really started the other problems, so I'll figure those out as they come.
Sure. Sounds good. All right. I think I got some. There might have been some typo, like just wording typo of the midterm. So I'll update that and send you guys an announcement if there's corrections. And if I get more corrections, yeah, I'll do that. I'll try to update as we go. But I think everything is solid mathematically. It's just some little typos. All right. Sounds good. Thanks for coming. See you guys on Monday.
Yeah, thank you.